let's see, yeah. So, I guess, welcome everybody to my presentation about the throughput-oriented sparse matrix vector multiplication on a processing and memory system. So basically, first of all, sparse matrix vector multiplication is a fundamental kernel in industry and academia, and it's used in sparse neural networks, graphs, and other physical and chemical domains, for example. But the problem on commodity systems is that random accesses to the input vector result in cache misses, and that makes the kernel fundamentally memory bound on those systems and leads to a low hardware utilization and inefficient computation. So our goal for this work was to basically develop a high throughput, low latency, and high efficiency implementation of this kernel. Observation that led to this goal were that processing and memory can actually alleviate data movement for those type of kernels, but doing a single SPMV implementation on a processing and memory system does not really scale to the large size of the system. So a key idea for this work was to basically divide the PIM system resources across many different clusters and to do basically parallel SPMVs in order to basically take advantage of the numerous PIM cores that we have access to and the memory capacity and achieve our goal of throughput-oriented and high-efficiency implementation. Our results are that basically we can improve throughput on average by 93x over the latency-oriented version, so the single SPMV implementation, and achieve a utilization of computing resources of 73%. So this is the UpAmp system, so basically a state-of-the-art real PIM system that we're using, which consists of a host CPU and some main memory, but also some PIM memory, so DRAM with processing cores close to the data, which we can access to do our computations. If we want to do SPMV on a distributed system, like a PIM system, for example, we have to distribute the workload somehow, and that's basically done by partitioning the matrix. We can either do that horizontally, so row-wise, and then multiply with the entire input vector, or do it in a vertical fashion, so column-wise, and then access only some parts of the input vector. But also it's possible to do a combination of both, which is then called a 2D partitioning system. But how is it actually then the SPMV performed on this UpAmp system? So first of all, we partition the matrix according to a format that we've chosen earlier, and then transfer the matrix and vector data onto the PIM memory, so from our DRAM to the actual processing and memory, and then we execute those kernels simultaneously, and after they're all finished on those DPUs, we retrieve the resulting output vectors and stitch them together back in host memory via the CPU. So, as I said, doing a single SPMV on the UpAmp system doesn't scale really well. So, for example, if we just use one DPU, we can see that initially all the time is basically spent on computation because one DPU has to do all the work. But then it scales rather well to 32 to 64 DPUs. But then we see the overall execution time starts to increase again just to the total amount of data that we're basically transferring to and from to the system, which consists of the input vectors. So basically it does not really scale beyond that point really well. Other observations that we basically make are that balancing the number of zero element entries of the matrix across the DPUs is really important to achieve a consistent equal kernel time across all DPUs. Minimizing the total data that needs to be transferred to all the DPUs is also really important to achieve a low overall execution time. I found out the best performing kernels for our specific workload, and also did an automatic selectation algorithm to basically determine the kernel of choice for a given SPMV, which consists of the partitioning format and storage format that's being used. But our core mechanism is, as I said, we we just select a few DPUs to do a single SPMV by clustering them into a single cluster, and then one cluster is responsible for one single SPMV. That way we can do many independent SPMVs at the same time to support like basic concurrent users or concurrent tests. And also SPMM workloads are another application. And by doing this, we basically provide sufficient load to each DPU. We tested the results, and basically on a selected set of matrices that have vastly different properties and come from different backgrounds. So because it's a general purpose implementation, and we used an UPMEM system configuration of 2,500 DPUs over the whole system. What we were able to observe is, like I said in the beginning, a 93x average throughput improvement, ranging from 57x to about 259x, depending mostly on how many number of non-zeros matrix has. So the single SPMV version works better for larger matrices, since then the penalty isn't that large. The latency just decreased by 3x for this test, but we can actually do sort of a trade-off between throughput and latency, depending what our goal is. By basically using more DPUs to compute a single SPMV, we can decrease the latency. But if we basically use less DPUs, then we can do, per SPMV, we can do more at the same time, and thereby increase throughput in theory. What's interesting is that we see basically diminishing results at both extremes. Basically for large cluster size, we have insufficient loads per DPU, and that way it doesn't make sense to use too many DPUs per SPMV. But if we use just a really low number of DPUs for one SPMV, then basically the total amount of data that's transferred is really high, and the memory bus is overloaded. If we compare it to CPU and GPU implementation, we can see that in NVIDIA A100 GPU achieves a really high throughput, but that's only the kernel time. Oh, yeah, once. Oh, okay. So the kernel time, and exactly. So the UPMEM system is basically comparable to a CPU performance, but what's really important is that the utilization is a lot higher in our implementation. Basically, for GPU is less than 1%, and for our system it's about 80%. So we are fundamentally limited by the PIM system of basically, since it's just a prototype, like first version implementation, and but basically the PIM system has the potential, by improving those PIM cores, to achieve higher performance in the future, since it's fundamentally not memory bound, but bound by the arithmetic throughput of those PIM cores. And it's a highly efficient basically implementation, whereas the CPU and GPU won't see similar benefits in the future just by increasing the hardware performance. Thank you very much, everybody.
Do we have any questions for Lukas?
So you mentioned that your performance mainly depends on the number of non-zeros, right?
Yeah.
So did you see any characteristic based on the sparsity pattern? Because like if you're all non-zeros on the diagonal or upper top, this kind of things, do you see different performance? Because this is how you are distributing the non-zeros, right?
Exactly, so different partitioning formats then have a different effect on how the performance basically behaves. And I've also, like I said, I did an automatic selection of the kernel that we are supposed to use based on matrix properties.
Okay.
I did some analysis regarding some properties, for example, if the matrix has like a block pattern, or if it's a scale-free type of matrix, and that way a specific kernel is selected. I just didn't have too much time to go into those specific kernel selection methods, but there are different kernels that are implemented, and they are basically, we use this like a good kernel for a given characteristic of a matrix.
Okay, I see. So do you do any pre-processing, like reordering the data, this kind of things, or maybe do you think in the future? So you will have a more structured sparsity.
Oh, so the thing is, the matrix data for a sparse matrix is either stored in basically a sparse storage format, so COO, CSR. So
no, I didn't mean this. Like if you do some reordering of the non-zeros,
I think for those formats they're already ordered. So for CSR, I think, right?
I think
What
it's
do you mean?
different. I'm gonna talk to you offline, okay?
Yeah,
It's
great.
a different term. Thank you.
Well, in the interest of time, let's thank Lukas.
Okay.